So we're talking about the RSA crypto system. Like the two other cryptographic schemes we've studied, it's based on elementary number theory. And Diffie-Hellman key exchange and the El-Gamal public key crypto system. These were based on the difficulty of computing the discrete logarithm. Now, there's another problem in number theory that's hard. You might not think it's hard, but it really is. It's simply the problem of factoring positive integers into product of primes. Now, the fundamental theorem of arithmetic says that every positive integer is a unique product of primes. So in principle, if I give you a number like n equal 97813600021, I don't know. Well, make it easier. 2, 4. So we know it's not a prime, but we want to factor it. Now, that's hard to do by hand. It's a big number. How big is it in words? It's like 9,781,360,024. It's a 10-digit number. Well, it's only 10 digits. Now, you might not be able to factor it by hand, but you might expect that maybe Maple can factor it for you. And in fact, Maple probably could. So let me see. Let me just switch to Maple for a moment. Share screen. So there's a command in Maple called ifactor. The I stands for integer. This is to factor an integer. And what was the number that I just said? It was 9,781,360,024. Huh, wow, look at that. So that wasn't hard for Maple. Maple's the number is a product of 2 times 2 times 2 times 1217 times the number 1,004,659, which is actually a prime. So 2 cubed, 1217, 4659. Huh. Yeah. So we could factor it. But in fact, as numbers go, this is pretty small, because it only has 10 digits. A number could have 10,000 digits. A number with 10,000 digits, that'd be a lot harder to factor. Let's see. Maple's pretty good, actually. So you might think that it's not so hard to factor, a computer can do it, but in fact, this really is the fact from experience. Computers are not yet powerful enough to factor very large numbers. Quantum computers might be, but they don't exist yet. Yet the very, 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 very expensive, complicated quantum computers that have been built only can solve really very, very trivial problems. So if one could build a quantum computer, there are quantum algorithms that can factor large numbers, but conventional computers, supercomputers, everything we have now are not able to do that. And what has been the most widely used cryptographic scheme is based on the difficulty of factoring. Even in the simplest case, suppose you're given a number n, and you know it's a product of two primes. So given n, which is known to be a product of just two primes, find P and Q. That's the problem. And this is, so far as we know, too hard for computers. So even if you have the significant additional information that your integer n is a product of just two different primes, find the primes, the computer can't do it. If P and Q have just, let's say, 10,000 digits, it's not so big, 10,000. It's way too hard. Okay. So you might say there's an element of religious belief in this. You have to believe that it's hard to factor. But you don't have to believe it. Whether you believe it or not, it is hard to factor. And as far as we know, no one, not the CIA, not the British intelligence, not Russian intelligence, no one knows how to break a code based on this difficulty of factoring, because somehow they've learned how to factor large numbers more efficiently than anyone else. So I haven't explained yet what the cryptographic scheme is. All I'm saying is that there is some cryptography that's based on the difficulty of factoring integers into a product of primes. Right? And what is the kind of cryptography we're interested in? There's a kind of a method which is called public key cryptography. So the idea is the following. Alice wants to send a message to Bob that everyone will intercept the message, but it's encoded, and no one else should be able to decode it, to decrypt it. So Bob or someone publishes the encryption method. So the whole world knows how to take a message M and convert it into some ciphertext C. Everyone knows how to do that. So Alice has a message M, which using this encryption method that everyone is told how to do, computes C and transmits C to Bob. And Eve, who's eavesdropping, intercepts C. She knows what C is. So she knows that somehow, not somehow, she knows exactly what Alice did to obtain the ciphertext C. But somehow, knowing how to obtain that ciphertext isn't enough for Eve to intercept the message, right? But Bob can do it, right? Bob has published his key. He can do it. So you can imagine how this might be useful. Let's say that, it's World War II. And all through Europe, people are fighting the Germans. And there are partisans, people in occupied countries who are fighting the Germans, collecting information. And they want to help the Allies fight the Germans by sending them information. So they need a way to encrypt the information. And we don't know who these people are who want to help us. We just know there are lots of people out there who are collecting information on German troop movements, and they want to send it back to the Allies. The US, the British, the Russians, whoever. So what we do is we publish to the whole world an encryption method. We say, if you want to send us a secret message, here's how you encode it. So these people, and we don't know who they are, but anyone who wants to send us a secret message, once they have the key, this public key, this method of encrypting, they can take their message, encode it, and transmit it. Now, the Germans are intercepting all messages. The Germans are like Eve here. But even though they know the encryption method, they're not able to decrypt it, to decipher it. Right? So for a long time, it was a theoretical possibility, but no one had a way to create such a public key crypto system. How do you create an encoding scheme, an encrypting scheme that you can tell to the whole world, so anyone, everyone, everywhere can take a message, encrypt it, and send it to us over the radio, whatever, anyway. And these three guys at MIT, Ravesh, Shamir, and Edelman, came up with a method, and it was based on the fact that if I give you primes P and Q, then you can multiply them to get a number n. But if I give you n, and you want to find the two primes that you multiply together to get n, that's effectively impossible. Right? So it's easy to multiply two primes to get a number, but given a number, even if you know that it is a product of two primes, it's impossible to factor it. So I'm going to the RSA crypto system is a method to use this empirical fact from number theory as the basis for a public key crypto system. Right? And it is used constantly, for example, for almost all internet commerce. It makes buying and selling things on the internet possible. But you can use a credit card, encrypt the number, and in a way that only the receiving company, Amazon or whoever, is able to decrypt it. Okay. So what is the arithmetical basis for this? So let's start with Fermat's little theorem. Fermat's little theorem says that if P is prime and an integer A has greatest common divisor 1 with the prime, so A and P are relatively prime, then if I take A and raise it to the power of P minus 1, this is always congruent to 1 mod P. So for example, you can check. Let's say you take P equal 5. So what are the numbers relatively prime to 5? 1, 2, 3, and 4. P minus 1 is 4. So 1 to the 4th is congruent to 1 mod 5. What is 2 to the 4th? That's 16. 16 is congruent to 1 mod 5. What is 3 to the 4th? 3 to the 4th is 81. 81 is congruent to 1 mod 5. What is 4 to the 4th? Let's see, 4 to the 4th. 4 times 4 is 16, times 4 is 64. 4 to the 4th is 256. It's congruent to 1 mod 5. So that's an example of Fermat's little theorem in action. Okay. What is a proof of this? So let's see. I gave a proof yesterday, very simple proof, and let me repeat it. So suppose, if this is a theorem which holds more generally in groups, but if you just want to prove a to the p minus 1 is congruent to 1 mod p, consider the numbers 1, 2, 3, 4 up to p minus 1. So these are distinct mod p. Multiply each of these by the number a. So I get a, 2a, 3a, 4a, up to a times p minus 1, or p minus 1 times a. Okay. And I'm looking at all of these numbers mod p. So if I take two different multiples of a, if xa or ax is congruent to ay mod p, that means p divides ax minus ay, which is a times x minus y. So p divides a times x minus y. But the greatest common divisor of a and p is 1. And by Euclid's lemma, if p divides a product of two numbers and is relatively prime to one of them, it divides the other. So by Euclid's lemma, p divides x minus y, which is exactly what it means to say x is congruent to y, mod P. So if AX is congruent to AY, X is the same as Y mod P. Now here my X's are the numbers 1, 2, 3 up to P minus 1. They're different mod P. So these numbers are distinct mod P. They're P minus 1 numbers, distinct mod P, and none of them is 0. So these are just some permutation of these numbers. So 1 times 2 times 3 up to P minus 1. This is congruent to the product. This is all mod P. A, 2A, 3A up to P minus 1 times A. Now the product of all the numbers from 1 to P minus 1, this is just P minus 1 factorial. Here, if I take out the A's, I have P minus 1A, so it's A to the P minus 1, times the product of the integers from 1 to P minus 1 factorial, mod P. So P divides this difference, but P doesn't divide any of the numbers from 1 to P minus 1. So P is relatively prime to P minus 1 factorial. I can cancel it. So A to the P minus 1 is congruent to 1 mod P. That's a beautiful, simple proof of Fermat's little theorem. Now, there is a generalization of this due to Euler, which deals with the case when your modulus is not a prime, but a composite number. So suppose I take a number like m equal to 10, which is 2 times 5. So what are the congruence classes A up to 9, 1 to 9, such that A and 10 are relatively prime? What are the numbers relatively prime to 10, less than 10? 1, not 2, 3, not 4, not 5, not 6, 7, not 8, 9. So these are the numbers, or these are the congruence classes modulo 10 that are relatively prime to 10. So A is in this set of numbers. It's the same as saying that the GCD of A and 10 is equal to 1. And the number of these numbers, there are 4 of them, right? So the cardinality of this set is 4. And I claim that each of these numbers raised to, so let's define for any m greater than or equal to 2, that this is the Greek letter phi of m, be the number of integers a between 1 and m minus 1, such that the GCD of a and m is 1. So if you take the numbers from 1 to 10, these are the numbers relatively prime to 10, so phi of 10 is equal to 4. This function of m is called the Euler phi function. And Euler's theorem, which generalizes Fermat's theorem, says that if the GCD of a and m is 1, then a raised to the power phi of m is congruent to 1 mod m. Why is this a generalization of Fermat's theorem? If m is a prime number p, then the numbers 1 up to p minus 1 are prime to m, and phi of p is equal to p minus 1. So in this special case that m is a prime, Euler's theorem says that if the GCD of a and p is 1, then A to the phi of M, which is P minus 1, is congruent to 1 mod P. So you can see that Euler's theorem is a direct generalization of Fermat's little theorem. Let's just check it for this example. So 1 to the 4th is certainly congruent to 1 mod 10. 3 to the 4th is 81 is congruent to 1 mod 10. 7 to the 4th, let's see, what is 7 to the 4th? 7 times 7 is 49. 7 times 49 is 343. 7 times 343, 7 threes are 21, 30, is 2,401. And this is certainly congruent to 1 mod 10. And 9 to the 4th, what's 9 to the 4th? 9 times 9 is 81. 81 times 9 is 729. 729 times 9 is, I think, 6,561, which is also congruent to 1 mod 10. So this is an example of Euler's theorem. Now, for the RSA crypto system, I need only a special case of this. The special case is when n is a product of 2 primes, p times q. So if n is p times q, so let me just write down a row. So so this is the special case. We'll see. I'll explain why it's a special case in a moment. That is, if the greatest common divisor of A and PQ is equal to 1, then I claim that A to the power of P minus 1, Q minus 1 is congruent to 1 mod PQ. And in fact, I can improve this. I can make this exponent a little smaller. So P and Q are primes. Let's say they're odd primes. So consider P minus 1 and Q minus 1 and take the GCD of those two numbers. And let's call that, if I want to follow the notation in the text, let me call that G. So A to the P minus 1, Q minus 1 over G, I claim this is always going to be congruent to 1 mod P and Q. P and Q are distinct primes. P is different from Q. Right. Let's look at a nice example. Say, suppose I take P equal 3, Q equal 5. So PQ is 15. And the GCD of P minus 1 and Q minus 1, that's the GCD, the greatest common divisor. P minus 1 is 2, Q minus 1 is 4. The greatest common divisor of 2 and 4 is 2. So that's my number G. So P minus 1 times Q minus 1 divided by G is 2 times 4 over 2 is 4. So what this theorem says in this case is that if A is relatively prime to 15, then A to the 4th is congruent to 1 mod 15. What numbers are relatively prime to 15? So the GCD of A in 15 is 1. What could A be? A could be 1. So you have no factor in common with 15. So it's not numbers not divisible by 3 or 5. So 2, not 3, 4, not 5, not 6, 7, 8, not 9 or 10, 11, not 12, because 12 and 15 are divisible by 3, 13 and 14. So these 8 numbers are relatively prime to 15, and I claim each of these to the 4th power is divisible by 15. Let's check. So, of course, 1 to the 4th power is 1, and 1 is congruent to 1, mod 15. 2 to the 4th is 16, which is certainly congruent to 1, mod 15. 4 to the 4th, let's see, we already computed 4 to the 4th. 4 to the power 4 is 256. Let's see, 256 minus 1 is 255. And if I divide that by 15, I get a perfect integer, 51. So 256 is congruent to 1, mod 15. Let me take another number. Let's take 13. That's harder. What's 13 to the 4th? 13 to the 4th is 28,561. Subtract 1, I get 25,560. Divide that by 15. Didn't work. What's going on? 13. That's all right. 13 to the 4th power is 28,561. Subtract 1. That's 28,560. 28,560 divided by 15 is exactly 1904. So this number is divisible by 15. Okay. Why is this always true? Number 4. So if A is relatively prime to P and Q, then that's certain. So this equals 1. Then certainly P doesn't divide A, and Q doesn't divide A. So by Fermat, A to the P minus 1 is congruent to 1 mod P, and A to the Q minus 1 is congruent to 1 mod Q. So if I take A to the power P minus 1, Q minus 1 over G, this is the same as A to the P minus 1 raised to the power Q minus 1 over G, and G is a divisor. G is the greatest common divisor of P minus 1 and Q minus 1. So this is 1. This is all mod P. This is 1 to the power Q minus 1 over G, and 1 to any power is just 1. So A to this number is congruent to 1 mod P. And similarly, A to the P minus 1, Q minus 1 over G. If I look at this modulo Q, this is A to the q minus 1 raised to the power of p minus 1 over g, which is 1 to the p minus 1 over g, which is 1. So p and q both divide the number a to the p minus 1 q minus 1 over g, and these are distinct primes. So if a number is divisible by two different primes, it's divisible by their product, so this minus 1. So pq divides a to the p minus 1 q minus 1 over g minus 1. So a to the p minus 1 q minus 1 over g is congruent to 1 modulo pq. Pq divides this difference. And so why is this the same as Euler's theorem? So this is actually the practical result that we need. But in fact, let's see, if I take PQ, phi of PQ is equal to P minus 1 times Q minus 1. So what I actually proved was a little bit stronger than Euler's theorem, because Euler's theorem simply says that if the greatest common divisor of A and PQ is 1, then A to the power of P minus 1 Q minus 1 is congruent to 1 mod P. And what I actually proved is that a smaller exponent, this divided by G, also has that property. So that's certainly nice to know. Right? So how can we use this to create a public key crypto system? So I'm about to describe the RSA public key crypto system. And it's based on the fact that if I give you two primes, you can multiply them and get a number of the product, but I give you the product, you can't factor the number to find the primes. So here's what Bob does. So Bob is going to create a system where Alice can send him a message and Eve cannot figure out or decrypt the message. So Bob, chooses two secret primes. He doesn't tell anyone. Secret primes P and Q. So he knows P and Q. So he can compute, well, so he knows P minus 1 and Q minus 1. And he can certainly multiply them together to get some number. So Bob chooses secret primes P and Q. He computes this number, and he chooses an encryption exponent E, such that the greatest common divisor of E and this number P minus 1 times Q minus 1 is equal to 1. Bob also computes the number capital N, which is P times Q. And what Bob sends to the world, Bob publishes the following two numbers, N and E. So what Bob sends to the world, and in particular to Alice, is a number N and a number E. So this is public knowledge. This is not a secret. All right. How did Bob get these numbers? He secretly chose two large primes P and Q, multiplied them together to get N, and he publishes N. He doesn't say what the factors of N are. He just gives the product P times Q. And he chooses a number E, which is relatively prime to the number P minus 1, Q minus 1, that he can also easily calculate. Okay. Now, Alice has a text that she wants to send. So in cryptography, this is called the plain text, M, which is a number. Right? Alice computes. What does she do? She takes M, raises it to the power E that Bob published to the world, and reduces it mod capital N. And that number, C, so you choose C congruent to M to the E mod N, that's the encrypted message, and that's what she sends back to Bob. Right? So here is the picture. Bob runs a full-page ad in the New York Times and says, here are numbers N and E. If you want to send me a message M, compute M to the E and reduce it modulo N to get a number C, and send me the number C. And I claim that I can decrypt, I can decipher from C to get the message M, but Eve or any other enemy listening in cannot decrypt the message. So how does Bob decrypt the message? So because E is relatively prime to P minus 1 and Q minus 1, Bob can calculate, he does this privately, he's not telling anyone. He calculates a number E, number D, this is his decryption secret, such that ED is congruent to 1 modulo P minus 1, Q minus 1. Right? So if E is relatively prime to this number, you can solve the linear congruence, ED congruent to 1 modulo that. And then what does Bob do? Bob computes, he got the secret message C, he computes C to the power D modulo N. What is that? So C to the D, C is M to the E, this is M to the ED. ED is congruent to 1 mod P minus 1, Q minus 1. So ED is 1 plus some number, P minus 1, Q minus 1 times, I don't know, call it T. So this is M to the 1 plus P minus 1, Q minus 1 T. This is all mod N. This is M times M, the P minus 1, Q minus 1 T, mod N. But m to the p minus 1 q minus 1 is congruent to 1 mod n. That was Euler's theorem. So this number is just 1. So we get m mod n. One also has to check that the GCD of m and PQ is 1. But almost every integer is going to be relatively prime to PQ, and you can figure out if your number is not relatively prime to it and just change your message slightly if you have to. You're asking, can Alice decrypt the plain text? She doesn't have to. She knows the plain text. That's her message. But if she forgot her message, she would not be able to figure it out. So if she only had the same information, if she only had the ciphertext C, she'd be in the same situation as Eve. She would not be able to decrypt the message.
That's what I mean. Thank you.
Okay. But that's a very good question. Now, how can you decipher the message? Bob can decipher it because he knows P and Q. So he knows P minus 1 and Q minus 1. So he can solve the congruence ED congruent to 1 mod P minus 1 Q minus 1. Eve could break the code if she could factor n into P times Q. But if she cannot factor n, she cannot decipher the message. So this scheme is based on 100% on the fact that factoring the number n, you know it's a product of two primes, but you don't know, you have no efficient way to compute those primes. Right? So there are nice examples of this, and let me go through one. And of course, I'll pick the one in the text. This is easy for you to follow as well. So here's an example of an RSA crypto system. So Bob has to choose two primes, P and Q. So let's say he picks P to be 1223 and Q to be 1987. So then he multiplies them to get the number n. So n, P times Q, is 1223 times 1987. So that's the number 2,430,101. So Bob publishes this number. He tells the world n is 2,430,101. Then Bob chooses the encryption exponent. It's a number e, which is relatively prime to P minus 1 times Q minus 1. So he wants a number e, which is relatively prime to 1222 times 1986, which is a number e relatively prime. Let's see, if you multiply this together, you get the number 2,426,892. And Bob picks a number relatively prime to this, and the number he picks in this example, he chooses E to be 948,047. So he also publishes this number, 948,047. 047. So these two numbers are given to the world. These are public. Everyone knows these two numbers. Okay. Now, Alice, like everyone else in the world, knows these two numbers, and she has a message she wants to send. So here's Alice. And she has a message M, which is 1,070,777. That's her message. This is the plain text. So how does she encode this? She wants to take M to the power E mod N and reduce that mod N. She gets a number C, and that's her encrypted message. So C is going to be 1,070,777 raised to the power E 948,047, and reduce that modulo N, which is 2,430,101. And if you calculate this, you will get that this is the number 1,473,513. So that's the number C that Alice sends to Bob. So the number that's going forth from Alice to Bob is 1,473,513. And of course, Eve intercepts that number. So Eve knows capital N and E, and she also knows the ciphertext C. And she wants to get M, right? But she can't. She can't, but Bob can, because Bob is able to compute the decryption number D. Right? So P minus 1 times Q minus 1 is this number 2,426,892. Bob can solve the congruence DE congruent to 1 mod P minus 1 Q minus 1, which is the same as solving the congruence. And see, what is E? E, everyone knows E, it's 948,047 times D has to be congruent to 1 modulo 2,426,892. But this is just a linear congruence, which you can solve quickly on a computer. And you get that D is equal to 1,051,235. So that's D. And this is C. And so everyone knows C, only Bob knows D. If you take C to the power D, which is M to the E to the power D, which is M to the 1 mod this, that's going to be M mod N. So what Bob does is he takes the encrypted message C, the ciphertext, raises it to the power D, reduces it mod N, and it's this 2 million number, and out comes the message. Okay. And that is the whole idea of the RSA crypto system. So N and E N is the modulus, and E is the encryption exponent. And D is a number such that D times E is congruent to 1 mod P minus 1 Q minus 1. E is the encryption exponent. D is the decryption exponent. Right? And that is the story. Now, in order to decrypt the method C, you need to know P minus 1 times Q minus 1. What is P minus 1 times Q minus 1? That's PQ minus P minus Q plus 1. PQ is equal to N. This is N minus P plus Q plus 1. So everyone knows capital N. If Eve could know, so everyone knows what P times Q is. If E could figure out what is P plus Q, she could also compute PQ and P minus 1, Q minus 1. But there's no way to know P plus Q. Okay. Now, let me point out something which at first isn't very obvious if you want to use this RSA crypto system. You start off with primes P and Q, your secret primes that you multiply to get N. But how do you find these large primes? It's actually not so easy. It's a finding large prime numbers, in fact, is hard. Right? In fact, there are companies whose business is computing and selling large primes. If you want a prime with 1,000 digits, that's hard to get. And there are companies that do computer searches, very sophisticated ones, to find large prime numbers, and you can buy them. For one thing, if you're using the RSA crypto system, you don't want to use a prime too often. So somehow, if it's occurring too often, it could become easier to break the code to factor your numbers if you know what possible factors might be. So there actually is a large-scale industry computing and selling prime numbers to people who want to implement the RSA crypto system. So if you have a number, how do you know if it's a prime? Well, one way to know if it's a prime is, if a number is prime, so let's give a simple example. If N is an odd prime, not 2, then 2 to the n minus 1 is congruent to 1 mod n, or if you like, you could say multiply by 2. 2 to the n is congruent to 2 mod n. So given n, if 2 to the n is not the same as 2 mod n, then we know n is not prime. And in fact, this extends to any number a. If the greatest common divisor of a and n is 1, then a to the n congruent to a mod n if n is prime. This is Euler's theorem. Sorry, it's actually just Fermat's theorem. If n is prime for every number n, so this is going to be true for all n. If n is prime, then a to the n is congruent to a mod n for all numbers a. So if this congruence is satisfied, we say that a is a witness. Oops. A is a witness to n being prime. A to the n is congruent to a mod n. This doesn't mean that n is prime. It's really an implication in one direction. If n is prime, then for every number a, we must have a to the n congruent to a mod n, if n is prime. So if you want to test whether a number is prime, you choose a whole set of numbers a, calculate a to the n, and see if you get a number congruent to a mod n. If you do, then your number n might be prime, but not necessarily so. If it fails even for one n, then you have proven without a doubt that n itself is a composite number, it's not prime. All right. And this is a very simple example of a primality test. It doesn't tell you if a number is prime with 100% certainty, but it does tell you that if you fail one of these tests for some number a, then with absolute certainty, a is not a prime. There are other somewhat more sophisticated tests which also can prove that a number is prime, or at least prove when it happens that a number is definitely not a prime. Okay. Okay. That is RSA. That is a fundamental thing to learn in any cryptography class. And we're going to talk about this a little bit more next week. And there'll be a little bit more number theory that's involved in trying to understand factorization methods. Because for any of this to work, you have to know, if you want to try and break a code, certainly, you have to see what kind of algorithms allow you to factor a number. Okay. That's the whole story. That's the story for today, in fact. This is the RSA crypto system. And it's not on the midterm tomorrow, but with 100% certainty, it is on the final exam. And you really need to spend some time understanding it. Okay. I mean, it really is quite interesting. And what's especially interesting is how some number theory, which goes back hundreds of years, suddenly finds it to be extremely important in industry and commerce, government, and the military. That's very good. Okay. Anything else for today? Again, remind you, I have a 7 o'clock session tonight. If you have any questions.
Professor,
Yes. I'm sorry, do you have a question?
any tip for midterm review?
I'm sorry, I didn't understand what you asked.
Do you have any tip for midterm review?
I'm sorry, I still don't understand what you're asking. Can you put it in the chat?
Is there any review for the midterm? Any review for midterm?
Oh, a review for the midterm. I'll put one together as soon as in the next couple of hours, and then email it out, post it on Blackboard and email it out to everyone. I'll make up a review. I said yesterday I would do it, but I said I would do it this afternoon because I spent all morning teaching several classes.
How many proofs will be there in midterm?
How many proofs?
Mm-hmm.
Oh, maybe one or two, not very many,
Okay.
but there will be some.
Okay.
Professor,
Yes.
I'm sorry, I'm at work. Did you receive any email from Ariona Agay?
Who was that?
It was about the schedule for the midterm tomorrow. I sent it twice. I don't know. I didn't get any reply back.
How did you send it? Did you send it
the
via
first-
Blackboard, or did you send it to my Lehman
Both
email directly?
ways. Both ways. I
Okay,
send
I'll
it
check,
one
but
from
if
the
you send it
Blackboard.
by normal email, I will have gotten it. I'll check it as soon as we log off. In fact, I'll check it right now. Just 1 second. Let me
Thank you
see
so
if I
much.
can-
It was late last night that I sent it from my email.
okay, just 1 second.
No problem. Thank you.
Let's see. Anuri Ariasha,
Yes, Ariona Agay, correct.
how do you pronounce your last name?
Agay.
Oh, okay. So, yes, you can take it at 7 o'clock.
Okay, thank
Several
you so much.
people told me that they work during the day, so I said 7 p.m. tomorrow night, I'll post an exam for you to take on Blackboard.
Okay, thank you.
Okay,
Thank you.
Yeah.
Bye.
all right, bye-bye.
Thank you.
Hello, Professor.
Anything else?
Yes, I also sent an email about the exam. So about 7 p.m. if possible.
Your name is,
Willie Wonderful.
how do you spell your last name?
Wandago, AUANDOUANDO.
Okay. And you also work during the day tomorrow?
Yes,
So is 7 o'clock okay for you?
yes, Professor.
Okay, so I made a note of this. So at 7 o'clock, I'll post the exam again on Blackboard, and you'll take it. You can take it then.
Thank you.
Okay. Okay. Okay, I'll be well.
Would you be available today this evening at 7, right?
Yes. Tomorrow
Okay.
evening at 7, not tonight. The
Oh, you
exam
will-
is on Thursday, tomorrow.
No, I'm talking about when we have questions. You
Oh
said
yeah, I'll be on Zoom at 7 o'clock today.
it's the same link.
The same website, yes.
Mm.
Same login.
Okay, no problem. Because last time I logged in and I couldn't find it.
Well, every time I've been on at 7 o'clock almost every day for the last week or so, last 2 weeks.
Okay.
So lots of people were online yesterday at 7, so the link certainly worked. But I'll definitely be there 7 o'clock tonight.
All right. Good.
All right. All right. Be well, all.
All right. Bye bye.
Bye-bye.